participants of this webinar on e-course on atmosphere, and Dr. Sohanlal Jain, a very warm welcome on behalf of Space Education and Research Foundation. I would like to mention that this webinar has 4 lectures, and these lectures are like a series, and after each lecture there will be a questionnaire that will come on the participant's screen, and it will have 10 MCQ type questions, and you may fill those and submit. These questions will also remain available on our blog and Facebook. The name of the blog, most of you know that it is SERF Ahmedabad, and Facebook also with the same name. Before I hand over the mic to Dr. Sohanlal Jain, let me introduce Dr. Sohanlal Jain and his work to you. Dr. Sohanlal Jain is a very brilliant scientist of Government of India. He was born on June 7, 1946 at Ahmedabad, Rajasthan. He had most of his academic education at Udaipur University. He earned his BSc, MSc and PhD degree in 1967, 69 and 74 respectively. Before completing his PhD, he was offered an assistant professorship at Udaipur University, where he did teaching work in physics for about a year and a half before he got an offer from National Physical Laboratory, New Delhi, to work there as a scientist. In 1975, he joined that institute, and there he did extremely good work on atmospheric research. In fact, it will not be exaggeration to say that he is a LIDAR man. He has developed differential absorption LIDAR, he developed micropulse LIDAR, he developed heterodyne LIDAR, and these LIDARs plus many other instruments which he indigenously developed at National Physical Laboratory. He installed those at National Physical Laboratory and also at the Maitri Antarctic Station of Government of India, and a lot of good research work has come out from these instruments. Dr. Jain retired in 2006 as head of the Radio and Atmospheric Physics Division at National Physical Laboratory. After his retirement, for 5 years, from 2006 to 2011, he was an emeritus scientist. In his early research career, he had worked at NASA's Jet Propulsion Laboratory during 1979 and 1981, and he did a very good research work there as well. He has published 70 scientific papers in national and international journals. He has guided 4 research scholars for their PhD work. He has been PI for several international and national programs. To name a few, I would say IFCAR and NCOR and APN. In India, there is also there is a Turning Point program on TV, which is a very good educational program for science. He participated in 7 of those programs. He has authored chapters in 8 books on atmospheric science. He has done extremely good work, and now I hand over the mic to Dr. Somlal Jain. Dr. Somlal Jain, please.
Thank you very much, Dr. Vas. At the outset, let me thank Dr. Vas for giving a nice introduction and giving me this opportunity to interact with you people remotely and talk to you next 3 days about the atmospheric structure, its composition, and ozone and other things. So I think it is a good opportunity to interact with you. Today I will be talking, and the plan of my talk is the just some introduction about atmospheric composition, historical background, atmospheric composition, greenhouse gases, radiative forcing due to greenhouse gases, some measurements made at NPL as well as over Antarctica, and some conclusions. So as you all know that Earth's environment is constantly changing, the scientific evidence says that the natural as well as anthropogenic activities are the cause of the changes. Some of the important issues of the concern are on the mother planet are the global greenhouse warming, urban and regional atmospheric pollution, regional increase in tropospheric ozone and decrease in the stratospheric ozone, etc. The reporting of ozone depletion in general and ozone hole over Antarctica in particular witnessed an unprecedented surge of interest in atmospheric monitoring. So in next two talks I will be talking about the atmospheric composition, its structure including some measurements and third talk I will discuss about the ozone in general and ozone hole in particular. The nature has played a great role for the very existence of the life on the mother planet Earth. We are grateful to the nature for providing proper location of the Earth with respect to the sun, its right composition and right environmental conditions to support the life system. For example, if there is no greenhouse gases in the atmosphere such as water vapor, carbon dioxide and methane, the average temperature of the earth would have been minus 15 degrees centigrade, but due to presence of carbon dioxide, water vapor and CH4, the average temperature of the earth has made 15 degree plus, and which make the all difference to support the life system. For example, I take 3 planets, say Mars, the atmosphere is very thin and carbon dioxide is very low there. So the temperature of the Mars environment is minus 50 degrees centigrade. Can you think about the life there? While the Earth's temperature, the CO2 carbon dioxide is around the 0.03%, very low, but it makes the whole difference into the greenhouse effect is plus 15 degree and makes the life supporting system. If you take the Venus, it's a very thick atmosphere of carbon dioxide having almost 96%, and so temperature is almost 420 degrees. So I can say that, and you can imagine that this proper conditions make its earth habitable. But with the industrial and technological development, we are adding more and more gases and pollutants in the atmosphere, which in turn will raise the global temperature as well as sea level will rise. Nature is trying to adjust, of course, itself, but after all, there is a limit, and it is not bottomless sink to absorb the changes beyond the limit. It is high time to limit ourselves to protect the mother planet, the earth. There is some historical background about the development of the life in the system. Earth system is like this. Earth was believed to be formed about 5 million years ago. In the first 5 million years, a dense atmosphere emerged from the vapor and gases that even expelled from the degassing of the interior of the planet. These gases may have consisted of hydrogen, water vapor, methane, and carbon dioxide. About say 3.5 billion years ago, the atmosphere probably consists of carbon dioxide, carbon monoxide, water vapor, and nitrogen and hydrogen. The hydrosphere was formed 4 billion years ago from the condensation of water vapor resulting in the oceans of water in which sedimentation occurred. So the most important feature of the ancient environment was of the absence of free oxygen. That means there was no oxygen, and evidence of such anaerobic reducing atmosphere is hidden in the rock formation that contains many elements such as iron and uranium, which is not found in the very recent times. 1 billion years ago, say early aquatic organisms called blue-green algae began using energy of the sun to split the water vapor and CO2 and recombine them into an organic compound and molecular oxygen. This solar energy conversion process is known as photosynthesis. The high in the atmosphere, some oxygen molecules were absorbed, the solar radiations, that is UV radiations, and split in the single atoms, and these atoms again combine with the available oxygen there to form ozone, and which protects the Earth's environment. The thin layer of ozone that surrounds the Earth atmosphere protect the planet from the irradiation of harmful ultraviolet radiations. The amount of ozone required to shield the Earth from biological lethal UV radiations from 200 to 300 nanometers believed to have in the existence. Then I will be, the O2 level was approximately 10% during that time in the atmosphere prior to this time, and then presence of ozone enabled organisms to develop and life on the land started. So ozone played a very important role. We will discuss about the ozone in details in the next third talk. Now I come to the composition. So say nitrogen is almost 78% in the atmosphere, and it dilutes the oxygen and it is being diluted by the oxygen and prevents rapid burning at the Earth's surface. Then oxygen has next component, which is 21% and used for all the living organisms for the respiration, and it is necessary for the combustion and burning also. Then the third component is argon, which is only on the say 0.9% and used in the light bulbs. So this diagram shows nitrogen say 78%, oxygen 21%, the carbon dioxide 0.03%, and all other gases 0.07%, argon 0.9%. So carbon dioxide only 0.3%, but it helps in the plant use it to make oxygen, acts as a blanket and prevents the escape heat from the outer space, that is greenhouse space we will be discussing shortly. Then water vapor is 0 to 4%, and again this say at the equator and the tropical regions near the coastal areas, the water vapor is very high, of the order say 4%, but at the tropical deserts, if you go, it will be, or Antarctic or pole levels, it will be almost 0%. Then trace gases are in very small quantities. This slide shows the details of the various gases in the atmosphere. I have already talked about the CO2 and oxygen, argon this much, and from the 0.037% remaining gases is distributed like this. that is the CO2 0.035%, neon only 0.018%, and like these different gases. This slide shows again the different gases such as in percentage as well as the parts per million by volume. So I will not go in detail about this. So these are the complete list of the various gases in parts per million by volume and also their percentage in the atmosphere. The nitrogen and oxygen are the main components of the atmosphere by volume. Together, these gases make up approximately 99% of the dry atmosphere. The solar radiations which are coming to the earth can be divided, say, ultraviolet radiation to three different parts. UVA radiation, that is 400 to 315 nanometers. UVB radiations 315 to 280 nanometers. UVC radiations, that is 280 to 100 nanometers. So from your diagram you see that UVA radiations are mostly very little are being absorbed above ozone layer, and most of them reach to the earth. That is the whole makes the difference. It's used for the earth's heating. And then UV radiation, most of them are absorbed above the stratosphere, and most of them also absorbed in the stratosphere, and UVC all absorbed above and so it protects the earth from there, so the harmful radiations are not reaching the ground. See this, say, sun radiation, sun temperature, if you take 5525 degree Kelvin, then the most of radiations from that will be in the very low wavelength, very shorter wavelength, while the from earth, say 200 to 300 degree Kelvin, it will be in say radiation will be in the infrared regions. So this slide defines how the greenhouse takes place. Say solar radiations, most of them coming here. Some of them are reflected back from the space itself. Some of them are reflected from the surface of the earth, and some of them are absorbed here. When they are absorbed, it converts into heat of the earth surface, and then with the temperature around, as I shown in the earlier slides, say 300 degree Kelvin, it will emit in the long wave radiation in the infrared, and some of them will be absorbed in the atmosphere here, and they will be reflected back to the earth, and some of them will go up in the space and lost in the space. So this makes the whole difference, that it by trapping of long radiation in the atmosphere by greenhouse gases make the earth temperature high and make him inhabitable. This slide shows slightly better way the greenhouse effect. The solar radiation coming here, the energy is absorbed by the surface, and some of them is lost in the space by reflection, and the heat energy is then converted. The radiations are converted to the heat energy, causing emission in the long wave radiations, and long wave radiations also, some of them are lost to the space and some of them are reflected back to the surface, and it again gives more energy to heat the earth surface, and then again, so this goes on, and this is the way how the greenhouse effect takes place. These are the say in a other way that these are different gases in the atmosphere, and the radiation coming sun are absorbed by these greenhouse gases here and are reflected in all directions, scattered in all directions, and some of them come to the earth surface, and that is why the earth is being. Then the scenario of the various gases in the atmosphere in comparison to the pre-industrial era, say 1750, carbon dioxide was almost 280 parts per million by volume, while presently it is of the, I would say, 400 parts per billion, and It's say it's global warming potential is say carbon dioxide is say 1 we assume. Its lifetime is 100 years and its radiative forcing is observed say 1.79 watts per meter square. Methane was only 700 parts per billion or 0.7 ppm parts per million by volume, and it's 1.8 to 1.9, and it's 25 times more than the carbon dioxide, the global warming potential of the methane, and its lifetime is around 12 years, and its radiative forcing is 0.5 watts per meter square. Similarly, nitric oxide was 270 ppb parts per billion, and now it's 323 parts per BB, parts per billion, and it's 200, almost 300 times more than CO2, its global warming potential. So a very small amount will have a greater influence in the heating of the global warming, and its global the radiating forcing effect, radiating forcing is say 0.18 watts per meter square. Then tropospheric ozone was around 25 parts per billion pre-industrial era, and now it's around 30 to 50 parts per billion depending on place to place, and its lifetime is very say few hours to few days, and its global warming potential say radiating effect is radiative forcing is 0.35. And these are the different chlorofluorocarbons which are almost zero during the pre-industrial era, and now they have changed into PPTs, parts per trillion. And say if you take an example of the chlorofluorocarbon 12, this is now 530 to 550, and its global warming potential, you see, there's 10,900 times than the CO2. So it's a very great potential for global warming, and it's also responsible for the ozone depletion, which we'll discuss in the later talks. And its lifetime is around 100 years, and its radiative force is 0.1. Similarly, different gases are given here. The CO2 is the fifth most abundant gas in the atmosphere. The volume of the gas has increased by 35% in last 300 years. This is primarily due to the human-induced burning from fossil fuels, deforestation, and other forms of the land use change. The human-caused increase in its concentration in the atmosphere has strengthened the greenhouse effect and definitely contributed to the global warming in last 100 years. Carbon is also naturally exchanged between the atmosphere and life through the process of photosynthesis and respiration. So you can see that the CO2 from say 1960 to the present situation has increased to around 400, which was almost 300 during 1960s. Methane is another strong greenhouse gas, and it was since 1750 or pre-industrial era, it has increased almost 150%. Is a greenhouse gas and contributing to 18% of the global warming, and its methane makes far less in the atmosphere, that is 0.002%, but it's effective 20 times than the CO2. Human activities has contributed to the rise of the methane in the atmosphere, and some of the sources of the methane are the termites, and they eat wood and produce methane as a result of the breakdown of the cellulose in their digestion tracts. The clearing of the rainforest greatly impacts the termite population and in turn methane content of the atmosphere. When patch of the rainforest is clean, termites populations explode due to the ample food source left behind the main cause of this. So the main this is shows the what are the natural sources of the atmospheric methane. So you can say 76% is due to the wetlands, 11% is from termites, 8% from oceans, and 5% from hydrates. So this slide shows again the how the different gases has changed with time. Say CO2 like this, nitrous oxide from say 300 to around 325 since 70s, and the methane 1.5 to 1.8 from since 70s to this time, and chlorofluorocarbons of ours initially they were increasing very fast, but due to the Montreal Protocol and various scientific and international agreements, now it has been started to decline, and maybe by 2020 it will be very low and low, and we'll discuss about this also in the ozone talk. And these are the distribution which shows the what are the different sources of the greenhouse gases and what are the share by the emissions different sectors and the contribution by various countries. So you can see that China and United States have a large contribution to this emission. Say is 7,527 million metric tons of equivalent to CO2 by the equal to carbon by China, and almost similar with the United States, and different countries have different contribution. The India has almost 1,500 million metric tons. The major greenhouse gases from people activities means anthropogenic activities. That is the carbon dioxide is around 54%, methane around 30%, and other gases 9.8%, nitrous oxide very small 4.9%, and fluorinated gases 0.6%. This I already talked about the green radiative forcing by different components. CO2 has maximum, then the CH4 has 0.48, and then N2O 0.16, and halogen. In my slides, I have shown all these things. Particularly, the aerosols have a negative radiative forcing, and the ozone, of course, has negative as well positive forcing. Say stratospheric ozone has a negative forcing, while tropospheric ozone has a positive forcing. Overall forcing is around 1.6 watts per meter square. Due to the various gases, the temperature of the earth has risen in last 100 years or so, around 0.6 degrees centigrade, due to the increase of greenhouse gases in the atmosphere. This slide shows how the sea level rise in the last 100 or 200 years is around 4 centimeter, and there are different scenarios where they say the sea level may rise from few centimeters to around meter, and if it goes to this level, then many countries lying very low areas and may 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 sink in the sea. So we have to be very careful, and we are making many international efforts are being made to. So there are different scenarios how the temperature may increase with time, and by 2100, say some models say 2 degrees, some say 3, then say 4 or 5 degrees, but international communities are trying to settle the agreement, say Paris Agreement or like that, that the temperature of globe, so we should stop the emission such a way the emission should not be responsible for the temperature beyond 2 degrees centigrade. So if it happens, it's okay. Ozone we will talk later on. But we have tried to measure the ozone and surface ozone on Delhi, and we see that there are day-to-day variations in the ozone. Say one day it may go as high as 140 parts per billion, and other day it may be around 60 parts per billion. And again, daytime always it will be maximum, and nighttime it will be very low values. These are the conditions or where the measurements were made. The temperature of Delhi goes around 45 degree centigrade in the summer, while the 10 degree during the winters. And it's say July, August, September are the rainy season, and June, July, say May, June are the summertime, and winter times in January, February, March, something like that. And this is the where the measurements were there made in Delhi at the National Physical Laboratory. These are the instruments used for the measuring the surface ozone. In this, the UV radiations at 254 nanometers are passed through a sample and having a sample of ozone from the atmospheric air, and the ozone free sample, and the difference in the absorption coefficient at 254 nanometer by calculation will provide you the ozone concentration in the atmosphere. And you can see from this slide the measurements since 1997 to 2003 that during the summertime the ozone levels are very high, and this line shows where the 80 as per the WHO, the 80 parts per billion. If it exceeds beyond this is a health hazard, and most of the time in Delhi in summer and in November, December, the values are always about 80 ppb. This slide again shows how in different years ozone values over Delhi has changed. Say this slide shows from 1997 to 2006, and you can see during the summertime it's very high values of ozone. During some monsoon period or rainy season it's very low, and again because there is dry season in November, December is almost dry, so that's again a very high values of ozone. And these are the slides. So this slide shows how many times in a year the value of ozone went beyond 80 parts per billion. So now in 1998, it was almost 39 times beyond 80 ppb, while 2005 it went 205, 15 times. So it's a very serious problem for health hazard, particularly during daytime when the children and people go outside and inhale this ozone. This is eye irritation and a lot of other lung problems and other things. This slide shows that sometimes nighttime ozone also increases like this. This may be due to thunderstorms or some other activities. This slide shows the different places. We taken data from different places from different authors, and we found that cities like Delhi, urban areas, the ozone is very high. Where if you have take the rural areas near say Pune, it's very low values, and other places Ahmedabad is again a very high values, and Anantapur and say Gadanki, the values are in between. So it depends on the vehicular activities and industrial activities and like this. Then ozone also damages if the ozone is say beyond 40 ppb every few hours, then it damages, or the crop yields also affected by this. And there was a formula by UNO which says that if you calculate the difference between the ozone in an hour and 40 ppb, and some it over for many hours. And if it is say AOT 40 value, this is shown as AOT 40, and it's for beyond 300,000 pp hour, then the loss of crop is 5%. And these are the our own values when the from 1997 to 2006, how many times the ozone levels has beyond the limit, and which has affected the crop yield in the fields. This slide shows the average NOx concentration, and you can see daytime it's very low, while nighttime it exceeds, say in summer months it's very low, and in the winter months it's very high values of NOx. We have done because a case study where how the ozone, nitrous oxide, nitrogen, NO and NO2 changes during the Diwali time, and how the particular matters changes during Diwali time, because a lot of people put lot of crackers in the atmosphere. A lot of cracker activities are there in last 2-3 days during the Diwali festival, that is light festival of lights. And we have made observations during these times, say on 21st October 2006 and 22nd October 2006, during night time as well daytime, and you can see the O3 and NO3, almost the everything increases during the Diwali festival. The other days it was like this, and on Diwali days it's very many times higher than almost 20 times, and again this. And particular matter also increase almost 15 times than the normal day's activity. So nowadays even we are telling the students in the schools, college, or student in the schools that please don't use crackers, and even children has made and this point that they don't use much crackers in the atmosphere to protect the environment, because it's during these days lot of people have to go to the hospital and see the doctors for their problems due to the aerosols and the ozone and other things. This slides again shows various constituents measured over NPL on different days, and this slides again shows how the ozone concentration in October and November. This again so how the oxygen, this ozone level with respect to NO changes. So you can see that they are opposite to each other. The ozone levels goes higher, then NO levels goes down. Similarly, when the ozone, so these are just opposite to each other. So this is the ozone, this is NO, and this NO. Similarly, the other concentration CH4 is shown here, or non-methane hydrocarbons are also shown here, and here again CH4 non-methane hydrocarbons are shown in November 2006, and this is also October 2006. The material for this presentation was taken from various sources, and I sincerely acknowledge the same, and I express my sincere thanks to all of them for using their material. Thank you very much. And then we will go to you may have be interested to ask some questions, and we will take a question and answer session, and let us discuss if there are some questions there, please. And I am thankful to you having very nice patience hearing, and let me see how the questions are there. There are many people who are attending this conference, and the names are given here, and then there are some questions here. How ozone influencing the blood bioorganisms? This may also affect their growth, and that may be also responsible for the growth of the bioorganism, because as I said in my slide about the AOT 40, that so similar things has to be done about this, that how, because I have not done much work on that account, but one may go through the data and collect data with respect to bioorganism and see how the ozone influences the bioorganism. So maybe we have to do more work on that, but I don't remember much work has been done on that. To have present situation of ozone and carbon monoxide. Yes, we made some measure. The present situation of surface ozone is almost going on similar ways. Say sometimes it goes 120, 100 parts per billion, and so it's a very serious condition over Delhi, and one have to be very careful about the vehicle use, and particular daytime children should be avoided to exposure at the high values of ozone during daytime. So it's almost 122, and the carbon monoxide also sometimes we noted that goes up to 4 ppm, and otherwise it varies from 1 to 4 ppm. Continuous of the Sanjeev Dwivedi asked the continuation of the earliest question, what about the present scenario value of the tropospheric ozone over country? So there are not many measurements over other in the country, but there are few institutions which are carries on these measurements, and we see that the metropolitan cities has very high values, while the urban cities has reasonable well under control, and that's say not health hazard, but in metropolitan cities particularly is if it goes beyond 80 ppb, it's very serious, and one should be avoiding daytime walking. Then Abbas Bro, can we use for the disinfection from the microorganism? I am not aware about this. Please, I'm not done any work on the microorganisms, so I will not comment on that. Abhishek Vyas asked, what are the basic precautions one may take to avoid the excessive emission of greenhouse gases? This is we have to control the emission from the industries. We have to use the clean fuel in the vehicles, and also in the say particularly the chlorofluorocarbons, which are very much responsible, has already been stopped, and most of the countries agreed to reduce the emission, so that we will not be able to emissions should not be there in the atmosphere, so the temperature of our global warming doesn't go beyond 2 degrees centigrade. So most of the countries has agreed, even USA has also agreed, but 2 years ago when the President Trump came, he backed out, but maybe they will join again, and international community will be able to reduce the emission levels to control the global warming to 2 degrees centigrade or below that by 100. How authentic is the ozone data measurement by ozonometer or sun photometer? This I will show a slide in my third talk where I have compared the micropod Dobson photometer with the Dobson spectrometer and other instruments, and we found that they are at par, almost maybe 1 or 2% difference in the measurement of the by Dobson spectrometer and sun photometers, and so that's quite good, and I have used for 5-6 years that instrument also, and I was, to be very frank, I was the first to get that instrument in India, sun photometer and microtop, and we have regular measurement, we calibrated it many times, and results are very satisfying. I will show some results on the my third talk about the ozone column ozone measurements over Delhi as well over Antarctica, and and I will also show the slides how much authentic they are. The next, Mr. Hiteshi Bhatt asked that what is the black carbon and concentration effect on the atmosphere, because the black carbon acts as a again absorber of the radiation, and it's acts as a greenhouse effect, and it again responsible for the greenhouse effect and global warming. So a lot of work has been done, and even the satellite data has confirmed by NASA and other places that the black carbon is very much responsible for the greenhouse effect or global warming. Why diurnal variation of ozone is high in winter than in summer? Uh, This depends on the here this humid. If the dry is more dry, then the values are very high. If it's less humid or less say more some humidity is available, some water vapors are available, then this is less. So there is a difference between summer and winter. Summertime is almost dry, and winter is that much not dry. So that is the that's why the diurnal variation during winter. Of course, winter as well as summer, the values are very high, but due to the say November, December in winter is high values, and May, June, April is high values in summertime. But so this is all the due to the difference in the humidity. Krishna Kumar asked, I am the process to write a proposal to ozone in the Bhutan atmosphere. Welcome, you should do that. That's a good cause, and you should do that, and we will support if there is a need is there. Then Prashna Subramaniam asked, thank you for your fantastic talk. It is any correlation between ozone variation and solar activity, particularly aurora effect in the Earth's polar regions? This I will talk about this in the third talk, because where I have shown that the solar effect, how much ozone variation is there due to the solar activity with respect to other constituents, say chlorofluorocarbons and other things. Do you then Orsini Saikya asked, do you have idea regarding natural increase of CH4 such as during the earthquake? Not much, but during the volcano, yes. Ravindi Havel asked, can you explain the detail how radiative forcing ozone plays cooling in that stratosphere and warming in the space? Because stratospheric, the ozone is absorbing the radiations, so it's doesn't allow the radiations to come down to the surface of the earth, so that's a, it has a cooling effect, while the tropospheric ozone has a greenhouse effect and it traps the in long wave radiation from the ground, and it's redirects toward the surface. So it's due to the greenhouse effect by the tropospheric ozone is warming, and while the absorbing of radiations by the ultraviolet radiation from the sun coming on the stratospheric ozone is absorbing, it protects, so this cooling effect. Krishna Kumar again asked, only thing as is there, I needed to gain one instrument like ozometer to measure ozone at different latitudes and altitudes of Bhutan in collaboration with Indian Research Institute. Please let me suggest for. So you can contact Mr. Krishna Kumar. So thank you if your interest in measuring these things, and maybe you can contact National Physical Laboratory for the collaboration, and they may help you. And this say for the whether you are interested in the surface ozone or only in the column ozone. So there are different instruments for both of them. For say for the surface ozone, you have to have the ozone analyzers, while the ozonometer you have the sun photometer or microtop, and that is not much expensive. Say Indian rupees, it may cost around 4 to 5 lakh rupees each. So you can have some collaboration with NPL or some other institutes, say IIT in Pune, or say Ahmedabad, PRL Ahmedabad, Physical Research Laboratory Ahmedabad. So you can contact them, and because I'm now almost superannuated, say maybe retired, so but I can help if you need any. Then Abbas Mirkhamlaw asked, Sir, Astronomy Department of Sommer State University, acha, he's from there, okay. I can make a comment about the astronomical observatory that they are very helpful for the observational side. Say India has a very highest observatory in the world, that is Henley, and this is a very good site of atmospheric measurement there. I have been there 3 times, each time spending almost a month and taking a lot of measurements, and maybe some I will show in my next talks. Can't excess CH4 be reduced? Others ask, can't excess CH4 be reduced to CO2 and water through some method to decrease greenhouse effect? Maybe one have to do some research on that. I have not done anything about that, and I cannot answer right now. But maybe some method you can find it out. But if you reduce the CH4 and if you increase the CO2, then again there will be another problem, because CO2 and water vapor, again they are the greenhouse gases. Of course, this is 20 times more global warming potential than the CO2, but still one may try by chemical reactions and something like that. Then Hiteshi again asks, is there any effect of Montreal Protocol on carbon dioxide? The Montreal Protocol is particularly for the ozone, and that was for the controlling the depletion of ozone, that is by reducing the chlorofluorocarbons in the atmosphere. And I will show you a slide where the Secretary General of UNO said that this is one and only one agreement in the world scenario which has successfully implemented, and that was the Montreal Protocol. So which successfully, and already ozone level depletion level has started to recover, and in 2002 I published a paper in Current Science, the recovery of ozone hole, and detail I will discuss later on. So yes, it was only about the ozone, not about the CO2. Um, Sir, how much reliable is satellite data as you stored all from the ground source? Because I made most of the measurements from the ground and surface measurements, so I saw that. But real satellite data uh, are not. You cannot have the diagonal variation from the satellite data. You can get on the average data. Say because it passes once a day. Through your day, maybe once a day or twice a day or something, depending on the orbit of the satellite. So you cannot get a reliable data, and that will also give the total concentration. And surface data will be not much reliable, but the total column ozone and that type of thing is quite reliable. And I will show that also how the in the my third slide, third paper, third talk, how they are reliable. And of course, the ozone, for ozone, the satellite data is very, very useful, column ozone and the ozone hole studies, because they track the ozone very nicely, and I will show that in my third talk. Krishna Kumar again say my internet connection went out briefly, so I could not hear from. My question was only thing, is there I needed to gain one instrument like ozometer measure ozone at different altitudes of Bhutan in collaboration with the Indian Research Institute. Please let me suggest for. Yes, you can contact either National Physical Laboratory New Delhi or National Physical Research Laboratory Ahmedabad, or Indian Institute of Meteorology at Pune, and you collaborate with them, and maybe you can invite them, or you can, so they can come over there. You can take them to different places, and they can join you to take observation at different place. So I think it will be collaborative program. It's very nice program to have collaboration, but you have to contact somebody officially with the National Physical Laboratory, or you can send me an email, so I can send you details about their contact number or email, so you can contact them directly. So yes, I think a good suggestion, you can do that. Then Mr. Mitrosa again asked, what is your opinion the ozone hole problem in the future? I think the ozone hole I will discuss in detail in the third talk, but as you asked the question, it's a nice question to be answered. The the ozone hole is only due to the chlorofluorocarbons when they go to the upper atmosphere in the stratospheric heights. Till they are in the tropospheric height, there is no problem with them. They have a very long life. They were actually the chemicals which were mostly appreciated, and they were known as amazing chemicals during 1920s when they were invented. But now they are most a hated element in the world, and so when they go up in the atmosphere and transported to all over the globe, and they go to this polar regions, what happens that their conditions become such in winter time that the temperature goes below 80 degrees centigrade in the uh, stratosphere, and some stratospheric polar stratospheric clouds are formed due to the very low temperatures if it goes below 70 degrees centigrade. And the over surface of these and clouds, some heterogeneous chemical reactions takes place, and reservoir, the chlorine stays there as a reservoir, and because there is a vortex formation around globe due to the around the polar regions due to the very low temperatures, and so the ozone rich air cannot enter that, and so due to this but as soon as the sun rises, the chlorine from the reservoirs or released, and they attacks the ozone, and one chlorine atom uh, can molecule can destroy almost as much as 10,000 molecules of ozone, and thus you can see that this is responsible, chlorofluorocarbons are responsible for that. So now with the Montreal protocol, the chlorofluorocarbons has already been reduced in production, and most of them have already stopped its use also. And so by the but because I shown in my slides that the lifetime of these chlorofluorocarbons is of hundreds of years, so it will stay till whatever is released in the atmosphere, they will stay in the atmosphere about the 2050 or so. So the recovery of ozone hole is expected by 2050 or so. Why ozone is decreasing while NO decreases? This is chemical reactions, due to the chemical reactions. Then Mr. So again asks, what is your opinion the ozone hole problem in the future? So I think ozone hole problem will be sorted out with the as I suggested that due to the Montreal Protocol and its adjustment and amendments in the protocol year to year basis, and international community already decided and it's implemented very successfully, so it will be ozone will be recovered by 2050 or so. Can we stop here? So thank you very much, everybody. I think we have a very good interaction and very question. I think you will be happy with the questions and answers. And if you have some more questions, you can write to me at my email, that is sohan46, and I will try to. Why ozone decreasing? Okay, it's already answered. So let us stop here, and we'll see you tomorrow. Thank you very much for the patience.